Hi, just as looking at the nature of what the sunrise and sunsets are like and the sun's motion across the sky, we know that the sun rises in the east and sets in the west, just like the stars. But over time, the sun drifts slowly eastward relative to those stars. And what we're watching here is the diurnal motion of the sun rising in the east and setting in the west to very speed up over a course of a day. However, the eastward drift relative to the stars takes about 365.25 days to return to the same location in the sky. That's 1 year. And therefore, a leap day occurs every year, every 4 years, because that extra 0.25 days accumulates into 1 day. And so we calendarize that by adding a leap year once every 4 years. But the sun itself just slowly drifts over time. And so we have to see why it does that with respect to the background stars. So let's take a look. The Earth has an orbital motion that makes it look a little different. The rate at which the Earth goes around the Sun is different than the rate at which the Earth turns on its axis. That creates a difference in the position of where the Sun appears to be in the sky. The solar day is what we call noon to noon. That's what we call the day. Everybody says what time of day it is, and they say it's noon or 1 p.m. That's time according to the sun, and that is the expected diurnal motion. Well, the sidereal day, though, is the day according to the positions of the distant stars. We call the normal day, or the solar day, this way, but if we look at the sidereal day, it's shorter. It is shorter by about 4 minutes. That means that the Earth has to turn just a little bit more to get the sun back in position for noon to noon, right? Otherwise, if we were telling this time by the stars, we could do that. We could have said the day is defined by when, say, Orion is directly overhead, or this star is directly overhead at midnight or something, when it is due south or due east. If there was some particularly bright star that we could see all the time, maybe like Betelgeuse goes supernova or something, and we could see it in the daytime. It's possible that we could tell the time by Betelgeuse then, because if it lasted for centuries and centuries, and most of human civilization, or we had another distant star that we saw. But anyway, we tell the time of day by the sun. But the sidereal day is different. We have three diagrams, A, B, and C, and we have a position on the Earth, capital A, and capital A looks at the sun in the first image when the sun is at noon. So then what happens is, as the Earth goes around its orbit a little bit, right? So we change from that bottom dashed line to the dashed line it's moved up a little bit. And if we go all the way around but have A pointed in the same direction, meaning looking at the same stars in the sky, stars are much more distant than the sun, so therefore they appear to be fixed on the sky, as opposed to the sun, which appears to move with respect to these background stars. So the stars themselves appear to come back to the same point in the sky in 23 hours and about 56 minutes. Now then, you got to move around a little bit further around the circle, just about a degree, which is 0.986 degrees, which is about 4 minutes of time to get to noon on the solar day in the bottom one. So those are the differences between those two things. And as a result of this Earth's motion around the sun and the difference between the sidereal and the solar day, the sun appears to move around the sky. And it does so on a path, and that path is called the ecliptic, and that is the path the sun apparently takes in the sky because of the difference in time between the solar day and the sidereal day, and because that happens because the Earth is going around the sun. The sun traces a path that looks like that curve. The red dash thing is the celestial equator, which is the projection of the Earth's rotation, the Earth's equator out into space. And the reason that the ecliptic, which is the path the sun takes that around the sky, is different than the celestial equator is because the Earth's rotation axis is tilted with respect to its orbital axis. But more on that later. The zodiac are the constellations through which the sun passes on its path around the ecliptic. So we have the celestial equator, which is the projection out into space of the Earth's equator. We have the ecliptic, which is the path that the sun takes in the sky. And the zodiac are the constellations through which it passes. So let's look at those particular zodiacal constellations. In October, you see it's in Virgo. November, it's in Libra. December, it's in Scorpius. Most of December, though, it's in Ophiuchus. Different one. Sagittarius in January, Capricornus in February, Aquarius in March, Pisces in April, Aries in May, Taurus in June, Gemini in July, Cancer roughly in August, and Leo roughly in September. These are rough things, but you'll notice they all sound very familiar. Those are the astrological zodiacal constellations, and you're very familiar with them from people spouting about them, but this is what this means. That's all that it means. So let's take a closer look. We can look at the zodiacal constellations, and now we're taking a much tighter look. Now we're isolating the sun in this video at noon throughout a number of years. And we see the progression of the sun as we're going really fast. We're doing many days per month. And there we go. We see, I put the artwork up. I put the boundaries of the constellations up and the lines that commonly shown asterisms as well as the names. Now, of course, we don't see these artwork in the sky, the red boundaries in the sky, nor do we see the names or any of the lines connecting them. But the ecliptic is the path that the sun is going on, given at a given time of year, given date, shows where it is in the sky. It's kind of weird that that line seems to be moving, but it's not. It's the sun that's moving along the line, and we're looking at noon or 1 p.m. or noon, depending on what the daylight savings hour is, where the sun is we're looking due south every solar day. So we're isolating it solar day by solar day. If we were isolating it by sidereal day, then the stars would stay fixed and then the sun would appear to move. As you can think about it, just imagine that we're fixing the stars in the background, and the sun would then definitely seem to move with respect to those background stars and background constellations. Notice over that we've looked at a number of years. It's now on the simulation up to 2030, and we're maintaining the same constellations. The sun has maintained the ecliptic to greater or lesser extent for thousands of years. Now, the Earth's precession on its axis will change things, will change the position of the ecliptic, or more specifically, it'll change where the ecliptic meets the celestial equator. When we get to that point, that is the autumnal equinox. When we get to that point, that's the winter solstice. This is the vernal equinox or spring equinox. And up here is the summer solstice. And that's when the sun is highest in the sky at noon. That's when the sun is up for only 12 hours. And this is when the sun is up for the shortest amount of time during the year. And there it is. And video was used using stellarium. So let's go back again and look at it. And instead of moving through the sky, we can see as the Earth moves around the sun, we look in the direction of the sun, and it appears to be in these constellations. And the tilt of the Earth's axis of rotation with respect to that orbital plane means that the blue band that goes all the way around, is not the same as the orbital axis, which is the dashed line. That thing is tilted. So this kind of diagram is a little bit goofy. And still we can then look at it from the other perspective to say, well, what's in the night sky at midnight during these times? It's like, oh, okay, so in September, Pisces is up at midnight. In December, Gemini's up at midnight, or at least 100%, 180 degrees away from the sun in the sky. In March, Virgo is 100%, 180 degrees. Why am I saying 100%? 180 degrees away from the sky from the sun. And in June, Sagittarius is up. And this gives us rise to what we see as the summer constellations and the winter constellations. Gemini is a winter constellation, Sagittarius is a summer constellation, Pisces is a fall constellation, Virgo is a spring constellation. And this shows the zodiacal positions of the constellations at midnight. Again, we're not taking into account the difference between the Earth's orbit and Earth's orbit and its axial tilt. We're not taking into account with this particular thing, but we do in this diagram. See, now we're seeing in this diagram where the positions of the winter and summer solstices are, where the autumnal and vernal equinoxes are. The vernal equinox occurs when the sun is traveling on the ecliptic and it crosses from south of the celestial equator to north of the celestial equator. It's also where we define the right ascension and declination of the equatorial coordinate system. If we look at it from a purely geocentric standpoint, which we shouldn't, I mean, I guess it's very helpful in this regard, because now we can look at what we apparently see, and we see that in the sky, straight up from the Earth's axis of rotation is the north celestial pole, the celestial equator is the extension of the Earth's equator out into space, and the sun appears to make a path in the sky that is tilted 23.5 degrees. But really, that tilt is actually the Earth's orbit around the sun, and the axis is tilted with respect to 23.5 degrees. So this is the geocentric view of things, but really we should have a heliocentric view, which we've shown, but this helps us understand what the ecliptic is and why it seems to go up and down based on how we appear to see it. Once again, geocentrism is dead wrong. Let's look again for the reason for the seasons. Frequently, when we look at the seasons, we say, oh, it's warmer in the summer and cooler in the winter. For the northern hemisphere, it's warmer in the summer. For everybody, it's whatever summer it is, it's warmer in your summer and cooler in winter. Why is that? So what is the reason for the seasons? Reason for the season is the tilt of the Earth's axis with respect to its orbital plane. The altitude of an object off the horizon is the height of that celestial object measured at an angle above the horizon. And the sun has a higher altitude in the summer than it does in the winter in the northern hemisphere. And the solstice are the points on the celestial sphere where the sun reaches its northernmost and southernmost points. And in the northernmost points, that's around June 21, and the southernmost points in the winter solstice, that's about December 21. The equinoxes are the places on the celestial sphere where the sun crosses the celestial equator. That's about March 21st for the spring, and the autumnal equinox is about September 22nd. So let's see what the effect is on that. When we look at the sun on the solstices, well, actually, yeah, on the summer solstice specifically, the sun appears to be very high in the sky, it casts very short shadows, the earth is warm, the sun is warm, and it rises very far north of east, and it sets north of west. And when it's at noon, it is high in the sky. That's belied by those kind of simulations I show, which will look at the sun. But if you think about it, the sun in the previous simulations looked high in the sky at noon when it was in the summertime. Well, we didn't take into account the fact that the sun rose and set. We were just jumping forward 24 hours at a time in that simulation. But if we watched the sun, we would see it would rise very far north of east, get to that high point, and set very far north of west. And so notice that the length of the shadows is short, and the days then, therefore, because the sun is in the sky longer, would be longer. That's important to know. But the short shadows are a key. Next, we can look at the winter solstice. Obviously, since the sun rises south of east and sets south of west, and it gets lower in the sky, the shadows are in general longer, and the sun is up for shorter periods of time. It's a very familiar thing, the winter days as they approach, the days get shorter. And the sun rises later and it sets earlier, and that's what we see. That's what we see here. So in the winter solstice, the sun is not up above the horizon as much. And at the equinoxes, the sun rises due east and sets due west. And that's the effect of this tilt of the Earth's axis and the Earth going around the sun. All right, so why do we care about shadows? This is why. Because the angle of incidence of the source of light on the Earth distributes the light differently. If something is beaming straight down on a surface, the light doesn't spread out that much. And in fact, the spot is smaller. But if there's a larger angle, then the beam of light, all the light gets spread out onto a larger surface area. So when you have the sun straight up, the beams of light do not spread out over larger surface areas, and therefore you have more intense heating per square inch on the surface of the Earth. That's what the left-hand side flashlight idea is representing. But in the winter solstice, when the sun is low to the horizon at noon, the sun's light is spread out over a larger surface area per square inch. And therefore, it is less intense per square inch, and therefore there's less, the intensity of light is less, which means the energy that is received by the ground is less per square inch. That means there's not more energy and it doesn't get as hot. That's the reason for the seasons. It is the angle of incidence of the light on the Earth distributing the light less and less intensely at winter than it does in the summer. Let's look at that effect on the next slide. Here we see it quite explicitly when we look at the left-hand side. The effect of that flashlighty thing on the left is that the smaller ground area is covered by the light from the sun for the same amount of rays of beams. Let's say you have 3 beams, they would hit a smaller surface area, which means they would be more intense and deliver all their light into a smaller surface area, which means that surface area would get more energy per square inch on the surface. In the wintertime, or late in the afternoon, or even late in the day when the sun is setting, it's actually less intense. Why? Because the light from the sun is being spread out per square inch over a larger surface area, and that's what we see on the right. So in the wintertime, it's all day like this. And it's always like this at sunrise and sunset for every day of the year, but at noon. Let's just look strictly speaking at noon. At noon in the winter, it's like the right-hand side, and at noon in the summer, it's like on the left-hand side. The intensity of the light is what creates the heat, that heat capacity per square inch on the surface of the Earth. And that's where the seasons come from. It is not due to the distance between the Earth and the sun. In fact, we are closer in the northern hemisphere to the sun during the winter than we are at summer. And that's just the position of it's the nature of the ellipticity of the Earth's orbit, which is very small, very small. So if it were about the distance, then we would be hotter in the winter. Or it's not. The angle of incidence of the sun's light on the surface of the Earth drives everything. That's what we have as the reason for the seasons. They're caused by the relative tilt of the Earth's axis with respect to its orbital plane, and it's not due to the distance from the sun. All right, so we talked a little bit about the zodiac, we talked a little bit about rising and setting of the sun, we talked about the sun's motion throughout the day, the sidereal day, the solar day, all of these things. We'll talk to you next time. Hey, if you like this video and other videos like it in my series, please leave a thumbs up and subscribe to the channel. I'm going to be going through and redoing a lot of my old stuff and doing a lot of new things too in the coming time, so please stay tuned. See you next time.